Alright, so this is going to be day 2 of properties of parent functions. So hopefully the other day you finished the day 1 properties with the worksheet. These are the functions that you're going to be looking at today. So we've got the sine function, so a little bit of trig. We also have cosine function, absolute value function, and then of course these are the formulas that would go with them. So when you get your worksheet, go ahead and match those up. We also have this one here, which is called the greatest integer function. So it's a very interesting one. We also call this a step function sometimes. The idea is that each of these is rounded to its greatest integer. So let's say that you, on the x-axis, we're talking about 0.5, so you're talking about a half. Notice that a half, after you go over a half, and in this case take the greatest integer of it, the greatest integer of a half is, what is this? 1. Oh, so this must be the least integer, let's see. Because if I went over 0.5 and it's saying it's at 0, yeah, this means we're rounding down. So, round down. Sometimes they'll talk about the rounding step function, and this one, even though it says greatest integer, is actually rounding down, because again, notice that every one of these decimals leading up to the number 1, and then not including the number 1, are rounded to 0, and then after that, anything that is between 1 and 2 is rounded up to 1, anything that's between 2 and 3 is rounded to 2, and so you get basically no decimals. So, greatest integer function is what they're calling that, but it's also a rounding down function. Sometimes they'll call it rounding up. I forget. There are a few other names, but usually you don't see step functions a lot unless you're talking about fixed rates or things like that. So anyway, that's just one to note that they do exist. We also have the logistics function, which we will be exploring quite a bit in one of our chapters. And then we also have the square root function. So that's that guy there. So again, you're writing each of these in the function name and then also in the formula. We're going to go over one of these for the second half of this worksheet. So we're going to be doing this one here. Let's see, this one is the cosine function. So you can see it matches up here. It goes through the y-axis at 1, and that's what this one does. So this is also the image that your calculator would give you if you graphed the cosine function. So we're going to call this the cosine function, and we're going to mention that it's cosine of x. What happens is, for writing purposes or typing, they won't put the parentheses around it. I personally like to put parentheses around because otherwise it just looks like it's its own term. So cosine of x, put it in parentheses. All right. So this one here, we're now looking for our domain. Remember that domain are x's, so how far left and how far right does it go? And you can see that it will in fact go on forever. So we're going to have negative infinity to infinity, and we're talking about all of the x's that are between that being included. The next piece is your range. This gets interesting because you can see that the range stops up here at actually the number 1, and then it also stops down here at the number -1. So we do include 1 and we do include -1, so imagining the bounds there and the fact that we're doing y. Remember that it's included, so that's going to be a less than or equal to symbol. Alright, then if we look for continuity, yes, it is continuous. It doesn't jump or anything like that, so we're going to just mention continuous. Then they're asking for pieces or parts that are increasing and decreasing, and this is where knowing the value of pi is very helpful, because basically each iteration of pi, it's either increasing or decreasing. So we are going to end up kind of taking a minute to go over what each of those are. So in this case, starting from 0 to actually 3.14, you can see that it's about 3 and then a little bit to get down to this base here. So we are going to say that it is decreasing from 0 to and it can't decrease at a maximum or minimum. So less than x, less than, and we're not going to write 3.14, but we are going to write pi. And then if we look at the next piece, it's going to increase, and it'll increase from pi all the way to what would be, since you're having another pi, 2 pi. And you can give the decimal value if you would like. So increasing from pi to 2 pi. All right. The interesting part about this is that this is a repeated pattern, and so it turns out that you can add any amount of pi after that, and you will get the next piece. So technically, and we don't need to be that technical, but technically from 0 you could add, I'll actually do it over here. It's going to technically say 0 plus 2 pi k. That's saying that if you take the number 0, which would be right here, and add 2 pi to it, you'd get over here, and then however many k values of that. And actually we're going to put minus as well, because you can go backwards. Now if this doesn't make a whole lot of sense, that's because we haven't gone over the unit circle. But we will go over that. That's going to be your lesser value, and then between there is going to be x, and then it's going to be your pi, which we will add or subtract 2 pi k. Same goes for the other one, so you could technically say pi plus 2 pi k. K is just a constant, and then we could also add 2 pi k here. But if you at least get from the image which parts are increasing and decreasing, that's fine. So this red and green section is perfectly acceptable. All right. The next one is asking if it's bounded, and the answer is yes. And so we actually get to write the word bounded because it's bounded above and below. So we don't have to say bounded above, at, and below at. We can just say bounded. And then we're going to put the equations. So this one up here is y equals 1, that horizontal line. And this one is y equals -1. So we're going to say y equals 1 and comma y equals -1. All right, then we're looking for asymptotes, and there aren't any here. Yes, it's bounded, but it's not bounded by an asymptote, so we can say none. It asks if there's symmetry, and yes, if you cut at the y-axis this piece in half, it would reflect on itself, so it's an even function, and it's symmetric to the y-axis. Then they want you to find out all the maximums and minimums, and again, you can do it for just this image if you would like, since we haven't done a whole lot of exploration of our trig functions yet, or you can understand that right here is a local maximum, right, at 0, 1. And then it turns out that every 2 pi distance from that, either subtracting or adding, you're going to get another maximum. So from that 0, you can say that you could add or subtract 2 pi k, and you will get another maximum. For the minimums, at least one of the minimums that we see here is right here, and it's over pi and down -1. So pi -1 is that point. So you can say your minimum is pi -1. And then again, to that x value, you could add or subtract 2 pi. Oops, 2 pi k. Well, that's really awesome. I am getting a new stylus pen very soon via the Amazon. So hopefully my writing will improve a little bit. All right, so that's the idea, and again, each of these are going to be the functions that you are evaluating, so you're trying to find if there's asymptotes or what you're bounded on in certain equations. So, there you go.